Well, good day there, and welcome back to Faith, Culture, Politics in Australia with Mark. And just before I get going, this is a reminder to hit that like and subscribe button if you appreciate the content that I'm bringing to you, and if you have the means to support, maybe consider buying me a coffee as well. So I'm welcoming again David Denham, architect David Denham, and those of you that watched the last episode appreciated the conversation. And I'm just going to remind people of a quick clip from David from our last interview. Now I'll play that for you, which has had quite a bit of traction, and a lot of you have actually enjoyed part of it. So I'm going to play this quickly for you.
Well, I sent you a little while back an extract which I enjoy. I pulled, there it is. I don't know if you've got it pulled up, but it's pulled out of Hansard, which is our government state of record. And it is the number of times the CSIRO has been asked to produce empirical evidence that man-made carbon dioxide is causing catastrophic warming between September 2016 and March 2022. And in this is a whole stack of points which come out, and you've got things like the top line is CSIRO admitted that it has never stated that carbon dioxide from human activity poses a danger. Instead, statements of danger came from politicians. You've got another one. CSIRO admitted that today's temperatures are not unprecedented. It just goes on and on and on. There's 20, 30 of them. There's references from international scientists. So it's utterly disgusting that Hansard, which is the record of our own parliament, is embedded in that is the proof that our most eminent scientific body, which is CSIRO, basically, like what you and I are saying now, realises and will condone that it's all rubbish. And yet the politicians keep going. That's another thing that you and I will discuss at another time, I believe. It's why particularly left-leaning, and our Labor government in particular, is so enmeshed with this ideology and destroying the future of our country, the prosperity of our country, and our environment all in one foul hit. It really is disgusting.
So there you go, and I'm welcoming David again to the show. Good evening, David. Good to see you again. And
Yeah.
Yep, good, and we are. This is a follow-up to that earlier discussion. We talked a bit about the renewables. We talked a little bit about the destruction of our environment, our habitat, the wildlife. But a lot of people appreciated that they were not aware about that Hansard record. And as I said, there's about 110,000 just on my Facebook platform that have viewed that clip. So people are quite interested, and quite a few people are sharing it. So we had about 2,500 people felt that it was worth sharing, so they've forwarded that on as well. So people want to hear what you've got to say, David. So welcome back again, and as we unpack more of the science today in regards to climate change.
Oh, well, thanks for having me, Mark. And I hope people did enjoy it. The last talk we had concentrated very much on the cost of renewables against all the other sources of energy and the massive lies we're being told. And I cannot stress that enough. The lies are just paramount. They're huge. We're just getting bombarded with them. The whole thing is a fantasy. And the other thing, of course, was something that is not so much has been lied about, but it's been left out of the conversation, and that's the untold damage that's being done to our environment, the horrible damage from this renewable source of energy. It's the worst possible thing you could do to the environment, and we've been fed this thing where that carbon dioxide is a pollutant and is going to warm the planet catastrophically and kill us all. And to do that, they're killing koalas, they're destroying rainforests, we're killing 40, 60,000 bats every year. It just goes on and on and on. We're destroying our rural lands and our farmlands. And we're spending billions, if not trillions, of our money to do it. So Yeah, horrible stuff. So that's where we were. This time round, I thought we'd have a talk about and get on to a little bit more to the actual science, because I did think I mentioned it in this, that asking people when they give an impression of this ideology of climate change, who have they listened to? Who's told it to them? Because we're not fed any science at all. No one discusses it. I doubt if the kids at school are, because if you do pull out the science, as I plan to today, you're going to see that it would be impossible for carbon dioxide to do what they're saying. And so I'm going to go through the science. I will take, hopefully, us all through a little bit of a journey to get to a point where I'll be able to categorically show why carbon dioxide is doing nothing. So don't panic if they don't. Please, if you're watching this, don't panic if you can't remember all the numbers and the physical bits and pieces and the science, because you'll get to the point where almost it's irrelevant. But I think it is important that we should all understand the whole process of our climate, what causes it, the role of carbon dioxide, the role of temperature, how those two interact, and then expose some of the real scientific truth at the end.
Yeah, no, absolutely right. Well, looking forward to having that all unpacked. So, a little bit of a statement. So, according to the IPCC sixth assessment report, in the last 170 years, humans have caused the global temperature to increase to the highest level in the last 2,000 years. This current multi-century period is the warmest in the past 100,000 years, and they claim that man-made carbon dioxide is the main culprit. So, you're going to unpack that, aren't you?
Well, I'm going to destroy it. It's just another lie. It's absolutely not true. And the information's out there for anyone to have a look at and check.
Perfect. Now, last week we did talk quite a bit. So obviously, just as a bit of an intro, just a recap from last week, the destruction, this whole the use of all these rare earths and minerals and stuff all around the world. Now, there was some massive concerns about the biodiversity risks and the damage to environment and nature. We talk not just in Australia, but other countries. You wanted to talk into that a little bit before we get going as well, didn't you?
Well, yeah, if you want to pull up that first picture, this is just a segue from last week, if you like. And I did speak about lithium and batteries, and what we're looking at here is a lake in Bayanobo in Mongolia. And there's about 15, 17 rare earth sites all over the world. We've got a couple in Australia, which we're opening up now. And this is what they look like. For every ton of lithium, which we're using in all our batteries, we need 2,000 tons of spoil taken out of the ground. And that's got to be washed off with acids. And this is the result. And what happens, of course, for every ton of lithium that gets created, you get 1,341,000 gallons of putrid toxic sludge. That's been given off continually, but that would be for every ton of lithium mined, you get that pumped into the air, and It's full of sulfur dioxide, sulfuric acid, and hydrofluoric acid. And it's in this area we're looking at for hundreds of kilometers around this area. There's Chinese kids being born with birth defects. There's people dying of cancers left, right, and centre. It's and lithium is proving a disaster all over the world. I mean, for example, you can't get an EV onto a Scandinavian ship anymore. They won't allow them, because they spontaneously catch a light. They're terrified of that. So it's not good stuff. But so that's sort of my segue. I didn't have that photograph available last week, but I think it's good to make people aware that we are dealing with not only a horrible lie, but they're perpetrating something which is destroying this planet. So over the next few slides, I'll show you. I'll pull the science apart so people can get a bit of an understanding about the truth and how it really works. So if you want to pull up the next two, these are just two, you've got two temperature slides, which I'm going to pull up. One is, this is the tropospheric temperature of Australia. So taken from lowest troposphere, that's the 12 kilometres of atmosphere that we live in. We fly in it, all our weather is in it. That's really where it contains all our oxygen and carbon dioxide and everything else that's floating around. This is the air that we breathe. And in that, the University of Alabama Huntsville correlates all the weather balloons and also the satellites, and they've come up with this figure for Australia over just a 10-year period from about 2012 to about 2022. And as you can see, Australia's been cooling and carbon dioxide has been rising right through this period. So we are cooling in Australia. I'll make one point just here before we move on to the next bit. Look, the planet has warmed over the last 140 years. It's been warming naturally. We came out of a little ice age, which you're going to see graphs showing that in a little while. And it was really cold for some 400 or 500 years. Our oceans got very cold. And as we warmed out of that around 1750, all the ice, particularly in the northern hemisphere, melted and went into the oceans and got the oceans very, very cool. We're warming from that period. There's a lot of things which cause this warming, this natural change to our planet. We've got one of the big ones is Milutin Milankovic, a Serbian mathematician, 100 years ago. He plotted Earth's path around the sun, and it changes from circular to elliptical. There's the tilt of the planet, which is affected too. That doesn't remain constant. Our North Pole, by the way, is wobbling all over the place. It's quite likely within the next few years, few hundred years, it might be 1,000 years, the North Pole and the South Pole will absolutely flip, and they'll reverse. So the polarity of this planet, because we're a big magnet, will actually flip, and it happens frequently, about every 15,000 years. So all these things, it's a fascinating world we live in, and we've only seen a really tiny little bit of it as mankind in about the last 10,000 years. We've existed as a really prolific race upon this planet. So there's that. There's the paths around the sun. There's naturally all our oceanic currents. So we've got these currents that float around our oceans who have a huge effect on our weather and our temperature and how we exist. Everyone's heard of La Niñas and El Ninos and things like that. And we've got the El Nino Southern Oscillation in the Pacific. We've got the Pacific Decadal Operation, the North Atlantic Decadal Oscillation. So there's the Indian Ocean Dipole. There's currents going all over the planet which affect how we affect our temperature, our climate, and our weather. There's one also which is actually the sunspot activity, but I'm going to talk about that right at the end. It deserves its little piece all on its own because it's one of the most major causes of our climate, and no one talks about it. Poor little carbon dioxide really can't compete with some of these things. They're really so powerful in our climate. So, but anyway, we'll get to all of that stuff shortly. If you want to have a look at the next slide, I think it was a temperature gauge you've got of Wilcannia. Now I've thrown this one in because I want to say that temperature, and we're all being led on temperature. God, we're going to warm by 1.5 degrees or something, and we're all going to die. And I think if anyone's seen our previous talk, they may remember that Brisbane has an average temperature of 20 degrees Celsius, and the Gold Coast, because we're close to the ocean, so we have a slightly more stable warming effect than Brisbane, we're 21.3 degrees. So they're talking about us going from 0.8 of a degree warming over 100 years to 1.5. So that's only 0.7 of a degree. And yet the Gold Coast is 1.3 degree warmer than Brisbane. I mean, that's how ridiculous it is. Temperature is the most absurd way of dictating anything. At best, all it can do is form trends. What's been happening over the last probably 6, 7, 8 decades as our cities have grown is we've got all these fixed temperature gauges all over the cities, which contribute to this average world temperature. And they started off in a wheat field. And of course, as time have gone on, they ended up in a car park of a shopping centre and probably outside the exhaust fan from a Chinese restaurant. So, they're useless. And 70% of this planet is ocean. Well, we don't have temperature gauges all over that. So what they do is they make stuff up. They make up numbers. So temperature is an absolute farcical way of really measuring accurately where we're going. And the only thing is, this is one, Wilcannia here, which is in the middle of New South Wales, also almost the middle of Australia. But I'm prepared to say, well, look, this is a good indicator because it's not affected by oceanic warmth or temperature. It's in a very stable part of Australia, being right in the middle of a sort of almost a desert. Where the temperature gauge is placed is not affected by, it's not a big booming town turning into a city or anything like that. It's all out on its own on the outskirts of town in a very stable area. And as you can see, it's hot because it's in the middle of Australia. We've got, an average temperature of 26.7 degrees. Now, that's a pretty straight line, and that's in 140 years. So this is probably one of the most accurate temperature reconstructions that I've seen of really what has been happening in the Southern Hemisphere. Have a look at it. Nothing. We haven't warmed at all. There's the dotted green line of carbon dioxide rising from 280 parts per million in 1881 up to 410 parts per million. And what's the temperature doing? Nothing. So Wilcannia is quite unique. The only thing that might have affected its temperature change would have been carbon dioxide if that was doing anything. And obviously it's not. So here's a really good example that isn't, by the way, because of this, they've shut this one down now.
Of course they have.
They've had a few of these. They had a couple up in the Murray River. They had one at Wilson's Promontory, and they were all showing the same thing of no temperature warming in Australia at all. So all of those have been shut down now, and they're relying on the satellite. But when a satellite, you imagine a satellite's reading our atmosphere and reading kind of feedbacks. As it's reading it, what height is it reading? Is it kilometre above the ground, 2 kilometres, 5 kilometres, 20? Well, the troposphere is only 12 kilometres high. So, but what height is it reading? And at the time it's reading the temperature, what's below it? Is there a low weather pattern or a high weather pattern? Are we getting upwelling of hot air or downwelling of cold air or what? It's what's the weather like underneath when they're taking this temperature? It's absurd. Temperature is actually a very, very poor way of finitely telling us exactly what has happened or where we're going. But it's a guide, and it's the best one. It's all we've got. Just out of curiosity, the first thermometer with actually a scale on the edge of it didn't appear till 1750. So all the stuff we're getting before that is isotopes from lake systems or carbon dating from rock formations and things like that, which aren't bad. They do give an indication, but it's really only an indication. Unfortunately, I'm going to be using temperature gauges to tell my story because there's nothing else. But as I've just been saying, it's not a very good way of really indicating anything.
Yeah, absolutely. And you're 100% correct, because I mean, a lot of people that I've been listening to and talking to as well, I know Craig Kelly pushed this a bit, and Malcolm Roberts, calling out the farce of the Bureau of Meteorology, fudging numbers, and these weather, these temperature gauges in the areas. You know, we've got the urban heat effect. You've got these gauges near airports and all that. So everything that you're saying is already backed up by many other people and all around the world, of the impacts on these and how unreliable they are. But the most concerning thing that I think for most Australians or anybody that's going to be listening is the evidence that these people are fudging the data and the numbers, and that is massively concerning. And to what end? And that is what a lot of people are asking the questions about, is why.
Oh, NASA, even great organisations, and NASA does too. Later I'm going to be showing a graph which their representation of the energy budget of the world, and it's absolute rubbish. And I do know that some of the scientists in NASA are absolutely brilliant, and they're horrified. A lot of them are ex-astronauts and stuff like that, and they literally are tearing their hair out, because they'll do all the right scientific stuff and they'll come up with the right figures. And it's exactly the same with the CSIRO. It is full of great scientists. But you get someone like Larry Marshall, who was running the CSIRO, what they then tell us and what they write down for the IPCC. Even the people even the scientists who are in the IPCC are also often brilliant scientists who come up with all the good gear. But what is presented to the world, or what we are told, is absolutely someone's fantasy, who they twist it and will turn it and use words and stuff like that to bend the story to their ideology. And it's just rubbish, and it's very, very sad.
Very sad, absolutely right. Yeah. So moving on to, got the next one is global temperature and atmospheric CO2. Did you wanted to move on?
Yeah, well, first of all, I thought we'd just have a look at a couple of long-term graphs which show the relationship between carbon dioxide and temperature. The first one is over 400 or 500 million years. This has been done by geologists, so it's out of reading isotopes in rock formation, and it's been reproduced by different groups, and they're all fairly similar. But as you can see, the CO2 is the black line that starts at that circle, and I think
Cambrian region there. In the Cambrian region.
In the Cambrian, yeah, in the early Paleozoic. But this was when all the in that circle was when all we went through a massive growth period of foliage all over the planet, which eventually, going through the different periods, ended up becoming swamps. And right down the bottom, 300 years ago, we had this huge ice age, which crushed it all. And of course, all of that stuff turned into the coal, which we're using today, diamonds, and all our carboniferous layers. So that was in the Carboniferous period. So it's just interesting. So apart from that little blip of an ice age 450 million years ago, which no one is really sure what happened there, the one in the middle of the Carboniferous period, they still don't know actually what caused it. But you can see that carbon dioxide and temperatures are at the same level. But you can see to get there, they really took their own path. They did their own journey. And but they ended up there because at that cold, it was probably, it could have been movement of ice sheets. The Pangaea, the big land masses, hadn't separated at this stage. So ocean currents might have been blocked off, ice sheets might have started. It could have been our path around the sun. We really don't know. But it was a massive ice age, and that crushed all the material that was in the ground, which turned into coal and diamonds. And as you can see, it went on for a long time. And because the oceans or the water would have been freezing cold, a lot of carbon dioxide was sucked out of the air. And there's a little blip between the Jurassic and the Cretaceous, you can see. And that downturn in temperature there is probably when it's at the end of the Jurassic. And whatever that was, or whatever caused it, is probably what killed all the dinosaurs. So they still don't know exactly whether it was volcanic activity, whether it was the most common one is probably a massive meteor which covered the planet in ash for many years and literally killed everything, which would happen. So it's whatever it is, there it is. You can see it. It's shown up in the rocks. But you can see it's going in a totally opposite direction to the carbon dioxide. And then you get down to where we are, which is right on the right-hand side. We're sitting, it's actually a little bit higher than where it's showing. We're at about 14 degrees. That's showing about maybe 13 degrees, 12.6, 13. We're actually now considered to be 14 degrees. But a lot of that is, I think, just how people decide to gradient stuff. So, as I said, it's almost ridiculous to pick a number, and it's certainly not exact. So we're coming out of ice ages about even though it looks tiny, what you're looking at on the bottom there is 2.6 million years we've been in a series of ice ages. So the most important thing out of that is look how low carbon dioxide is. And as we came out of the last ice age, which is only, what are we talking now, about 14,000 years ago, which is not long, carbon dioxide was down at about 180 parts per million. We're only 420 parts per million today. At 140 parts per million, we're dead. Nothing will survive on this planet. So just only 40 parts per million would have killed every living thing on the planet. It would have killed all the plant life, which of course we eat both on land and in the ocean, or the fish eat in the ocean. And the whole planet would have been just like a desert. So we were very, very lucky. What we're doing now by creating carbon dioxide in our period of life, we're actually saving the planet. 420 parts per million is nothing. If you go down in a submarine, you're at 5,000 parts per million. Have a look at the gradient on the left-hand side. It's right up, and we don't notice it. If you go into a hall full of people and for 2 or 3 hours, that's probably 2,500 parts per million. So all we do know is the little rise that we have had in our last 140 years, which is 280 parts per million up to 420 parts per million. Our planet is blooming again. In the last 2 decades, with only a rise of 20 or 30 parts per million, the planet has greened by a further 15.3%. We need more carbon dioxide on this planet, not less. We very, very nearly became extinct. So this is, you can see as far as temperatures, look right through the Mesozoic area, the temperature was 22 degrees. And that is when all the current life forms of our planet, including the last lot of dinosaurs who were killed off, but all the birth of the main forms of our life force that we know today, both in the ocean and on the land, were all developed through the Mesozoic period. And that was at a land temperature of 22 degrees. And this planet was abundant. And we're worried. We're at 14 degrees, 8 degrees cooler, and we're panicking. We'll get over it. You know?
Yeah, and the real worry with that is people like, you know, his name gets mentioned all the time. Him and others are exploring the idea of you know, reflecting sunlight and cooling the planet, and you know, they're actually looking at doing worse. And from what we know is like cold kills more people than heat, and all these people are messing around, but for what? For, you know, this whole zealotry.
I know. Well, it's wrong. It's false. So. That's you can see all the wonderful periods of our planet when we had much higher temperatures and much more carbon dioxide. You can also see how they did their own thing. Yeah. They weren't together. You do get things at times at an ice age where the oceans will cool. They'll suck in more carbon dioxide because the colder the water at 0 degrees, the oceans are saturated at 1 particle of carbon dioxide per million. Up where we are, where the oceans might be at, say, 20 degrees centigrade, it's one particle or one molecule of carbon dioxide per 2 million molecules of water. So the hotter the water, the less it can hold. Like, you can prove this. Take two cans of Coke out of the fridge, open them both, put one on the bench and one in the fridge, and the bubbles in all of our soft drinks is carbon dioxide. And when you get up in the morning, the one on the bench will be as flat as a tack because it's warmed. All the carbon dioxide is being evaporated or expelled from it. The one in the fridge, even though it's open, will still be fizzy. So that's an experiment any kid can do. So it shows the colder the water, the more carbon dioxide it holds. So, anyway, let's move on. What's the next? What have we got next? Well, this is the period over the last. This is called the Holocene, it's an interglacial period. So it's if you looked at the extreme left-hand side, we're 9,925 years before now. Coming out of the Ice Age would have been about another maybe 300 or 400 years left of that. So we came out of an Ice Age to the beginning of the Holocene. We raised up quite quickly, very quickly. Then you see this massive drop. That's called the Younger Dryas, and which no one knows really what it was called. Could have been volcanic, could have been a meteor, could have been anything. Anyway, and then we go up to these two big peaks around 8,000 and 6,000 years ago, and that's when our civilizations were born. So those periods are known, and the Danish Meteorological Institute tells us this. Those periods were 2 to 4 degrees hotter than we are today. And it was when carbon dioxide was around maybe 200 parts per million at that stage. And it finished up on the extreme right just before us, say at the end of the Little Ice Age, at about 280 parts per million. So it grew right across this 12,000 or 9,000 years. While you can see the green line, temperatures slowly began to cool over that period. And they were certainly much hotter than we were today. You can see all the civilizations developed in these areas of warmth. So as I said, in warmth we prosper, in cold we die. So you've got the Minoan, which is the Greek eras. You've got the Roman warming, which is much, much hotter than today. And you've got the medieval warming. And if anyone watched our previous talk, that we know it's at least 1 degree warmer than it is today, probably more, because all the artifacts and bones where guys were buried and stuff like that, they're still in permafrost today. So that's on the extreme right hand. You can see that little red line just under 31. That's where we are right now. So you see the medieval, that's when the Vikings were farming Greenland about 1,000 years ago, and it's at least a degree, maybe 2 degrees warmer than we are today. We're not sure exactly how much. All of these were taken by a geologist, David Lappy, and he used, I believe he used some 30 to 40 independent methods of getting all of these temperatures. He used them isotopes of various minerals in swamps and all sorts of things, and it's considered reasonably accurate. And quite a few other geologists have done similar ones and come up with very similar figures to him. So it's probably a pretty reasonable representation of temperatures over the last 9 to 10,000 years. But as you can see, we basically cooled. We're much cooler now than we were, and all the time while carbon dioxide was rising. So, and you can see that little ice age, it goes for about 400 years. And you can see that right down the bottom at the minus 32. They're all minus numbers because they were taken from ice cores. So they were used as a representation of aerosol temperatures. out of the ice core. So minus 32 rising up to minus 31.5 on the right there. That's a rise of half a degree. It's just the way they did the temperatures. So, and and as I said, that was uploaded by Frank Neugebauer. So we don't know whether he's a relation of yours or not, but
coincidence.
David Lappy's, as a geologist, his representation is considered pretty accurate. So we can move on to the next one. What have we got next?
Yeah, so you got
have you got any queries on that?
No, look, it makes sense. I guess it frustrates me that they're getting away with this whole what you've just demonstrated, even just in that slide there about the cooling and that, and they want to continue to look at ways to reduce our temperature, which is actually worse for us as a species and everything else than anything else.
Well, Mark, think of that opening statement that you read out from the IPCC AR6, that we are in unprecedented warm times, and the planet has never been hotter in 100,000 years. Well, I think we've just destroyed that, haven't we?
Yeah. What a joke. What a joke. Come out with statements like that. Absolutely.
Right. Okay. Well, the next, what I'm going to go and do a little bit just on carbon dioxide itself. One of the things, and all scientists recognise this is not, left of centre or anything. It's just an absolute statement of fact. Carbon dioxide is a global warming gas. It does sit in our atmosphere currently around 400 to 420 parts per million. It would have a little effect of warming our atmosphere a little bit. I'm not sure that we could measure it, but it certainly would. But as you look, the more that you put into the atmosphere, the less effective it comes. So most of its warming was in the first 20 parts per million. And as you slide across that scale, you can see 60, 100, 140, 180, 220, 260, and so on. We're up at 420 now. So this was done a little bit for today. It was when it was at 400 parts. So the current deal is if you double the amount of carbon dioxide that's in the atmosphere today, so if you went from 420 to 840, you would have no discernible temperature change in the planet. Some people try and say, you probably get about a degree or 1.1 degree. And as I pointed out earlier on in this talk, so what? I don't agree with that. And a lot of scientists don't agree even with that. But 1 degree is not going to do anything. One of the things, as I said, apart from anything, we're 20 degree average here on the Gold Coast. Kansas 24.8. My son was a pilot with Emirates, used to go over to visit him at Dubai, and I'd be walking outside, it'd be just under 50 degrees. I didn't like it, but you could live in it. They did. So to switch that off. So anyway, there you go. So carbon dioxide does nothing. So we'll, I think, move on to the next one.
Yeah, we got that one there.
So this is a little bit more. This is the slide after this. I'm going to actually start talking about the electromagnetic radiation from the sun, which is sunlight as we know it. But these two are a little bit interesting because the left-hand side of the graph is the absorption of incoming solar radiation. So the sun hits the Earth at a uniform amount of energy. It's actually 1,366 watts per meter, and it comes in as a shortwave radiation. And I'm going to talk about electromagnetic radiation in the next slide, actually, because it's worth a little talk on its own. But as you'll see, a lot of the ultraviolet has been taken out. The red line is as it sort of came in, and you can see a lot of it's been missing. So it's been either reflected by the clouds, it's been absorbed by the atmosphere, or whatever, you get and this is as you get down to ground level, if you like, or sea level, you'll see that it's in terms of water vapor has absorbed a little bit of the infrared on the right-hand side. Not all of it, but some of it. Carbon dioxide has done nothing, and all of the others have done nothing. So then we'll move to the graph on the right-hand side. What happens is whatever is left gets into the ground or the ocean. Some of it is reflected off the ocean. So any of the shortwave radiation in the infrared band will be reflected by the ocean. But the leftover of ultraviolet will go into the ocean, and most definitely light. And we know that because if you've been a diver and you dive down in the water, you can see the light. It's quite bright, but it gets dimmer and dimmer and dimmer because the light, which is just electromagnetic radiation, is absorbed by the water and turns into heat. And you can see in that left-hand graph, there's quite a big lump in the middle there, the visible light. So that's actually what does most of the warming of water. So, but it also, the light will be absorbed in different color bands on land. So in the trees and the ground, depending on the color band. So you see what's reflected with the stuff that isn't absorbed. So if you're seeing something red on the ground, the red is being reflected back at you, whereas all the other bands of light have been absorbed. But once the electromagnetic radiation is either in the oceans or on the land, it is then re-emitted as infrared radiation only. What isn't reflected, it's emitted as infrared, and it's long wave radiation. So if you look right at the bottom of the left-hand graph, you'll see 0.2 to 0.3, 3.0. That's the frequencies of incoming radiation. If you look on the right-hand side, and my graph's gone off my page a little bit, you'll see it starts at 3 and finishes at 40 odd microns. So it's a much, much longer radiation wave. And here you can see that the red bit is the bit that escapes through our atmosphere or whatever we've got in it and gets out to space. The green big blocky bit is what water absorbs, and the various wavelengths at which it absorbs it. And the grey blobs are the bit that carbon dioxide absorbs. And you can see that little one, but if you look up above, there's very little energy. See, if you travel upwards to the graph, there's not much happening in those graphs. The main amount of energy is in the middle. And you'll see where the carbon dioxide is there, the grey one, it actually overlaps water. So they're competing against that wavelength. But you can see that water is far more effective because it's got a much wider band of wavelength than carbon dioxide. Very quickly now, I'm just going to throw some maths at you, which you don't have to remember, but just bear with me and I'll come up with a figure. There's 13 trillion tons of water in the atmosphere. There's 3.3 trillion tons of carbon dioxide. With all of these figures can be verified. So in terms of tonnage, there's about 4 times the amount of water as carbon dioxide in tonnage. However, carbon dioxide as a molecule has a specific weight which is 2.44 times larger than the molecular weight of H2O. So if you multiply 2.44 by 4, we're up to about 9, roughly. So you've got 9 times more molecules of water in the atmosphere than carbon dioxide. As a molecule, its ability to absorb heat, water is 5 times more effective than carbon dioxide from its specific heat, which is 4.8 over 0.8. So now we've got water as being 5 times 9, which is 45 times more effective than carbon dioxide as a global warming gas. But then when you go back to that graph again. When you look at the big area of green over that little area of grey, you could probably, it's hard to say. At this stage, I've had some people say it's 10 times more, and other people who know the figures say it's 20 times more. At worst, you multiply 10 by 45, water is 450 times more effective at its current levels in the atmosphere than carbon dioxide, or it's as much as 900 times more effective. So I've had scientists try and say that carbon dioxide is just as effective as water, as a greenhouse gas. It's absolute rubbish. So I've gone through the math. Please accept that I kind of know what I'm doing. And it's water is between 450 and 900 times more effective as a greenhouse gas at its current levels in the atmosphere. End of. So anyway, we'll move on from this one, because now we'll get to some of the more interesting stuff. Now, I've spoke about electromagnetic radiation. This is the stuff that the sun is blasting at us. There's the full band of it right across there. You can see it starts off, open it up. You're just closing off the screen a little bit. Where it's very close together on the right-hand side and zigzaggy, that's from the nuclear explosions on the sun. That's gamma radiation, and it's also X-rays. Then you get through, as it gets closer to the visible light band in the middle, you'll get ultraviolet, which is made up of UV A, B, and C. Then you've got the visible light band, which is, it's actually quite, because it's right in the middle of that curve. It's a big lump of energy. To the left of that, you've got infrared, and then you've got microwaves and radio waves. And that's where the wavelength gets longer and longer. So all the really big energy stuff is on the right, and there's slightly less energy on the left. So that's what makes up this electromagnetic wave. The interesting thing is, and I'll just throw this in, there's three main pieces of science which govern everything that we live, how we live, who we are, our planetary systems, absolutely everything. One is this electromagnetic wave. So that's how electricity and energy can be sent through space. But this is the same wave. It actually goes through a copper wire too. So it goes from cell to cell, from microns to microns. It's right through a wire as well. So the electromagnetic wave is something which transmits energy. The second thing is gravity. So two bodies are attracted to each other, equal to the product of their masses and inversely proportional to the distance they're apart. That keeps us standing on the planet. It makes something, when you drop it, it falls towards the planet. It keeps our planet circling around our suns, and it keeps our cosmos in balance too. So gravity plays a huge portion of how we live and how we survive. The third one is quantum energy, which is how a cell works, just between the electrons and the protons and the microns and how all the energies work. Now, the interesting thing is those three govern our whole planetary system. They're the main ones. There are others, but they're the three biggies. We don't know how any of them work, none of them. We can measure them. I've drawn you we've got a picture of one here, but we don't know how it works. So that electromagnetic wave, we know it's two-dimensional, so it works on multiple bands. It's not like a single zigzag like this. It can carry all these different types of energy in it, and they interact and work independently of each other, but are carried in the same wave. We don't know how that happens. We have no idea. We don't know how gravity works. We know it works because we're living proof. We're not falling off the planet, and our moon hasn't crashed down and crushed us all. So that's just an interesting little piece of stuff. So as this comes into our atmosphere at 1,366 watts per meter, All the stuff on the right, for the first bit of it, the gamma radiation, the X-rays, is all absorbed by our stratosphere, by the ozone in it. Some of the UVC, which would burn us, is too. Most of it is pulled out. What is left, some of the UVB and what's left of the UVC actually interacts with the oxygen and nitrogen in our atmosphere, and it does actually heat it. They say it doesn't, but it does, and it does it through processes called photoionization and photodissociation. Won't go into it, not important. So what's left is the bit of naturally light and naturally infrared, because we feel the heat. A lot of it is some of it is reflected from the clouds. So when you go outside on a hot day and it's a clear sky, you walk, if a cloud comes over, you feel cooler. And if you walk under an umbrella or a roof, you feel even more cool. So even though it's the same air on both sides, you're being sheltered from even more electromagnetic radiation. So we know some it bounces off. When it hits the water, some is also reflected. And we see that, glare. That's why we wear Polaroid glasses, when we're walking down by the ocean. And some of it is, and what is left is absorbed by the soil. So the UVB, as I said, what's left over of the UVB burns us, and we put on sunscreen. UVA, they put that in sunscreen too, but that causes long-term skin damage. Then we have the visible light, which allows us to see things, and that goes into the water, and that's the main source of energy which heats the oceans. The UV, the shortwave UV, bounces off the oceans, so it doesn't really heat it at all. So that's how electromagnetic rays go. So the sun. So we'll move on to the next one.
Yep. It's fascinating. People don't get to hear a lot of this unpacked really well. But the main thing, I want you to go back a bit and remember that whatever gets down there, whatever lands in the oceans or heats the oceans, whether it's light or UVA, when it comes off the surface, it comes off as long wave radiation. And I'll talk about that in a second. So this is how, when the sun hits our Earth, you can see only half of it is lit up, right? In terms of energy, if you and then you've got a circle. So right at the middle of the circle, the sun ray is at 100%. And if you imagine the rays hitting the poles, top and bottom, it goes to 0. So again, you can divide it in a half. A half times a half is a quarter. If you take a quarter of the 1366 watts per meter, you get roughly 341 watts. So you can now switch to the next slide. And if you have a look, see the yellow coming in there, incoming solar radiation is 340.4 watts. So that's just NASA's, what they've done is they've used this as to kind of talk about an Earth average. We know we've got 1366 coming in, but we know half of it's still asleep, so you can cut that by half. And we know some of it is 0 at the poles and 100% in the middle. So we've got another half, and that's your 340. So when you look at that left-hand graph, I'm not going to go into the numbers so much. They're really not that important. But you've got some reflected from the clouds, some on the left-hand side, go to the left, 77.1 down here on your left, some absorbed by atmosphere. You've got some reflected by the ground, which is, they've got reflected by the surface, the 22.9. That's actually kind of rubbish. It's a little bit ground, but it's really oceans. See, even though you've got oceans, they've got this thing hitting land. Most of what the IPCC talks about
is what's happening from the oceans, and I'll explain why in a minute.
Mm.
So you've got, see at the bottom there, you've got 163.3 being absorbed by the ground, if you like, and that would be a mixture of oceans and a mixture of water. And of course, that's 4 times as much at the equator and 0 at the poles, because there's nothing happening at the poles, and also nothing around the back because it's in darkness. So that bit is right. All of the rest of everything you're looking there is rubbish. So what NASA is saying absolutely makes no sense. I've spoken to a lot of people, and I've spoken to scientists. I said, can you explain this to me? And they can't. The only one who could explain it to me would have been the guy in NASA who wrote it and managed to get the thing published, because you've got 163.3 coming in, and see what you've got emitted by surface 398. Well, tell me how that happens. Energy is perfect. It's in perfect balance. Every watt per meter that comes into this planet ends up one way or another going out to space. Every single minute particle of wattage, the whole of the planet is in equilibrium. It's going to happen in different amounts. During daytime, it's going to be different from nighttime and all sorts of things, and you've got our weather is so different, and we live in different places. And I keep bringing up Dubai, where I'll go over to, you'll go for a walk in the desert in summer, and the temperature is the thermals coming off the sand, the heat coming off the sand is so hot, and the sand itself is so hot you can't walk on it because the air temperature is 48 degrees centigrade. But at night time, you go out there, that temperature of that will be 5 degrees because there's no sun shining on it. The heat, it's got some heat because the heat is retained by the ground, and that will take all night to dissipate. It never gets really cold, but it will get by morning. That sand will be quite cool. But it's, you go to deserts and look at minimum temperatures of the Sahara and things like that, they're 5 degrees. Whereas in the middle of the day, they can be anywhere from 30 to 50 degrees. So what's carbon dioxide doing? Isn't it supposed to be keeping the heat in? It doesn't disappear at night time. It's still there, but it's not trapping the heat at all. What does trap the heat is if you go to a tropical place where you've got humidity, an ocean, and moisture in the air, you'll find, I talked about last time, this place where I dived at Upi in the middle of summer, the air temperature, it's very close to the equator. It's right on the Morovo Lagoon, which is the biggest lagoon on the planet. It's the lagoon's shallow. It's only about 20 to 30 feet deep. So you've got white sand bottom. You can see all the energy coming in. You can see the bottom. And the air temperature at daytime is 28 degrees. The water temperature is 28 degrees. And at midnight, it's exactly the same because the water is keeping it static at that temperature. So unfortunately, but and what's weird too, it can't even be placed. At Dubai, you look at, say, where you've got a 50-degree temperature and boiling hot. Go further up the Arabian Peninsula, it's the same in the Arabian Desert. Scoot across the Arabian Gulf into Iran and go a little bit north, not too much, to Isfahan, and you're skiing. So this is what I'm saying, why temperature is so stupid. It doesn't even really matter about latitude. It matters on climatic conditions. It matters on moisture in the air. It matters with elevation of the land and all sorts of things, So temperature is such a poor way of really trying to see, sort of exactly what's going on. So, but carbon dioxide in all of those scenarios can actually be seen to be doing nothing. So take me back to the NASA graph again, and we'll get to the punchline of this whole story. All right. What NASA is saying and what the IPCC is saying is that this, from the surface of the planet or from the surface of the ocean, a long wave radiation, infrared radiation is being emitted. That rises up into the air, and it's got two methods of being trapped, one by water, and they say also by carbon dioxide. Now, we have seen that water is 900 times more effective than carbon dioxide, but let's ignore that for the moment. Let's say water's not doing anything. So what happens? This photon of heat with a certain amount of energy, which we'll call, let's give it a figure. It can be anything, 10 Googles, 10 pinpricks, 10 anything. It's a figure of 10 is emitted from the surface, and it hits the molecule of carbon dioxide. And a tiny little piece of it at around 14.8 microns, because carbon dioxide doesn't absorb and reflect back the whole range. We saw that. It only has that little grey lump in the middle, which is about it goes from 12 to 16.5 microns, but the main bit is around 14.8 microns. So the wavelength of the heat at 14.8 microns is redirected in all directions. Carbon dioxide doesn't hold onto it like water. We know water retains heat because we boil kettles and do all sorts of things. But carbon dioxide, it actually re-emits that photon, or that portion of that photon of heat, in all directions. So it happens instantaneously. By the way, everything I'm describing to you now is happening at the speed of light. So very, very fast and continuous. So that little micron, the tiny bit of it, that it's all going in 360 degrees in all directions, but a tiny little bit of it heads back to the surface. Now, what the IPCC says is that bit of heat heats the surface cumulatively, okay? And it happens cumulatively, and it heats it and heats it and heats it and warms it up till it's really, really hot. So it gets so hot, it evaporates more water, and seeing water is a really good greenhouse gas. That is what's rising our temperature. This is what the IPCC is saying. So let's have a look at that. So you've got 163.3 coming down, and see how you've got 398 going up. Well, we don't know where that figure comes from, except the 398.2 watts per meter is what a black body at 16.5 degrees, which is roughly the temperature of the average temperature of the surface, not the air above it, the surface, and that's the maximum it can emit. So that is what the IPCC is saying. It gets heated up. Now, I ask you, if you've got a garden and it's cloudy day, and so there's not sunshine on it, you've just got air temperature, and you've got a sunshade or something like that, do you find that the ground is hotter dramatically outside than if there's sun on it, it will be, but if there's not sun on it, it's the same temperature. And the air temperature inside your gazebo, it might be hotter inside the gazebo because hot air is getting trapped in it or something. So it just doesn't get hotter. But I'm going to describe it this way. And this is where the principle of thermodynamics comes in. Let's say that the heat being emitted from the surface, whether it's water or whether it's ground, is grey. It's like a grey paint, for example, but it gets evaporated and it can go up into the surface. If it was going to get hotter, it would have more black put in it, so it would be a darker grey. If it was going to get cooler, it would, say, have more white put in it, so it would be a paler grey. But let's say what happens. So we've got this grey of some depth coming out of the ground. It goes up. A tiny little piece of it is absorbed by carbon dioxide and re-emitted down. But now it probably, because of it's gone through an energy process, it's probably cooler. But let's say it's not cooler. Let's say it's the same temperature. It's going to be the same coloured grey as emitted from the surface, isn't it? Certainly not going to be darker. It'll only be at best the same colour, or it might be a little bit cooler. Under the laws of thermodynamics, all you're going to have is more grey paint. It's not going to be hotter. Adding, if you've got two groups of energy and you put them together, they will only change energy if one is hotter than the other. So one has to be hotter, and then the combination of the two finds an average between the two, and it depends on the amount of energy in each and also the volume of each. But you've got something being emitted from the surface at a certain amount of energy. That same photon of heat is being redirected back down to the surface. At best, it's the same temperature, or it might even be a fraction cooler because it's gone through some energy processes. So it's impossible for that energy to warm the surface of the planet. So I don't know, does that make sense to you?
Yeah, no, it does. Yeah.
Premise, what the IPCC is saying and what NASA is trying to say in that diagram is that the heat that after it's been emitted from the surface and being reflected down by carbon dioxide somehow makes the ground hotter, which evaporates more water and therefore causes the temperature of the planet to go up. Now, it makes no sense. But there's another really weird thing which they forget and no one talks about. Water in the atmosphere is a greenhouse gas, but you know what else it is? It's a bloody good umbrella. So if you look at when we get La Niñas, which is a La Niña is a dry wind on the eastern Pacific, but it's wet on the western Pacific. When we get La Niñas, they're warmer currents of ocean, so they evaporate more water. We get a lot of rain. We had a La Niña a few years back when we had the floods up at, it actually combined with Hunga Tonga, the water that was blasted up into the stratosphere, and we had lots and lots of rain events. So it actually makes us cooler. So Brisbane, when it's dry, and when the Gold Coast is dry and there's no cloud, it's hot. When it's cloudy, it feels humid. It might feel hotter, but the actual air temperature is not hotter. It's cooler. So water is an actual, probably a better umbrella than it is than a global warming gas. So they've kind of forgotten that. So the whole premise of everything they're saying is absolute rubbish. It's a lie. It cannot, by the laws of thermodynamics, it cannot happen. Something being emitted at a amount of energy being returned back at the same amount of energy, all you'll have is more product at the same energy. It cannot be hotter. It's impossible.
Well, they don't want to talk about that. They don't want to talk about thermodynamics and everything that you're bringing up here, because it's easier to sell people, hotter temperatures, messing around with temperature gauges and all these sorts of things, and capturing the media to give the same narrative. It's talking about thermodynamics and how it all works is not helpful to their cause. So they don't want that. They don't want to be talking about.
Well, they can't, and it's really weird. As I explained to you, I talk a lot with some of my geologist friends, and I'm saying, why aren't the other scientists? Because I wrote that piece which you've attached to our last talk, and it's gone out through Clintel and through the GSL Society, and that's thousands and thousands of scientists. And I've had some really great comments back and things like that, and people have picked on little things and stuff like that, but they've all agreed with the premise. And they said, yeah, of course that's right. So it's been ratified. I gave it to Ian Plimer too. I said, look, would you check this and make sure that I've got the science right? And he said, absolutely. So I don't know why we're not talking about this. It actually pulls the whole thing apart. So, but there's one other thing too I might throw in very quickly. So you've got the grey paint thing. You can't make grey paint any greyer by adding more, the same colour to it. That's number one. Number two, you've got, even if it did evaporate more water, it would probably cool us, not heat us. Number two, you've got the scientists telling you that carbon dioxide, it doesn't matter whether we double its current quantity, it's as a global warming gas in effect, it's going to have almost no effect. That's number three. Number four is the actual quantity of carbon dioxide in the atmosphere. There's currently 420 parts per million, right? I think that's 2,380 molecules of, 1 molecule of carbon dioxide per 2,380 molecules of atmosphere. But the IPCC is only talking about man-made CO2. They're not talking about the CO2 that's already there. So there's man-made is only 1% of the atmosphere. We're currently producing 35 gigatons a year. There's 3,340 gigatons in the atmosphere. So we're 1/100th of the atmosphere. So our man-made carbon dioxide is in the atmosphere at the rate, it's actually 1.1. I think it's 242,000 molecules of atmosphere for 1 molecule of carbon dioxide. There's bugger all there. It's a really, really poor global warming gas anyway, because it only affects a tiny little portion of a photon of heat at around 14.8 molecules. So you've got all these things that's saying it's almost impossible for it to do anything. So, but the big one is, I say, go back to number one. You take heat from a source, you return that heat at exactly the same temperature, that source will not be warmer. And so the whole IPCC premise, falls apart. So that's all the rest of the stuff, and the electromagnetism and all of the other bits and pieces are all fun. At least you know how we get there and how the sun shines on us and all the different frequencies do different things. But at the end of the day, it's just going to keep doing that. Carbon dioxide does nothing. So that's the bit that I would like anyone who's reading this to remember. If they're not sure, I've set it out in that piece that you've attached to our last talk, and I go through it. There's only four pages. There's 1 page of preamble, 2 pages of this very simple science, and 1 page of quotes from people like the United Nations and all of that, saying even what they're doing, they recognise that it's rubbish. So
and I'll attach that to this talk again as well. And it's and they're doing all of this and wrecking economies and destroying wildlife and destroying habitat and digging up rare earths and destroying the environment around there. All on this on what appears to be just a massive con on people. So yeah.
Well, it's a scientific lie, and it's very easy to prove. The last 2 slides, if you want to have a look at those, I've sort of saved them to the last because they're really interesting. And they're probably one of I've talked about all the things which do cause our weather, and that's the very much the oceanic cycles and stuff like that, but also the path around the sun, which varies dramatically. It's all cyclic, and one cycle interacts with another cycle. But there's another one which, and I find this one really interesting because it explains a lot of stuff that's going on. See all those zigzags up on the top graph there? Each of those is 11 years, and the sun emits these blasts of energy, and they're in an exact frequency of about an 11-year cycle. We don't know why it's 11 years, it just is. And they're bursts of explosions or energy which are nuclear in fashion, and they send a powerful blast of charged particles out into space, and they happen 11 years, and they're called sunspots. And we've known about them. Galileo first saw them, and we've been measuring them for 270 years. So we've got a pretty good indication of what they're worth. Now, the interesting thing is, when we're getting a lot of sunspot activity, our planet's hotter. When we get very low sunspot activity, our planet is colder. So if you have a look at the last few hundred years, the Maunder minimum, which you got 1600 and 1700, actually goes on. We started getting thermometers in 1750, but the rough, they're the ones with gradients on the side, but the thermometers were actually invented in the 1600s. And people were getting pretty good at working things out. So that Maunder minimum is the Little Ice Age. It actually goes back to about 1300, which isn't shown on this graph. But it's there was very little sunspot activity, and that was actually sort of noted probably from about the early 1700s by Galileo, or the late 1700s by the Galileo. But where they're blue, they're much bigger, and then they drop down again. So you've got that dip of the Delta minimum, which was 1800 in the 1800s, the early, which is true, that happened. Then it goes up and it drops down again in the 1900s. That one did actually have a name. It was called the Glassberg minimum. There it is down the graph below. And you go to the modern maximum. What is happening now is you can have a look at 2000. We're starting to drop. We're starting to go into a cold spell. And this is a NASA, if you have a look at the top, this is a NASA prediction solar cycle number 25, because we've been studying them and measuring them for 270 years. And they reckon we're probably going into another little mini ice age. And they've already named it the Eddy minimum, which you'll have a look at the graph beneath. Now, if you flick to the next thing, I'll show you what happens. And I just find this really interesting, but explains so much about our weather. The Earth is a big magnet. When you get a lot of sunspot activity, they're all charged particles. So what they do is they make the magnetic field of our planet really, really strong. Okay, so acting as a magnet, we become really, really strong magnet. The jet streams, which are around both poles, they're just showing the northern top pole, the Arctic pole at this stage, for this diagram, they're full of charged particles. So because the planet is a magnet, the charged particles around the jet stream will pull closer to the peak of the planet. So, and they'll zoom around, they'll actually move faster and get very close to the pole. It's called a stable polar vortex. When the magnetic field of our planet decreases because of low sunspot activity, which we're going into now, the magnetic field of our planet gets a lot weaker. So the jet stream, which you can see on the right-hand globe, becomes weaker and drifts away from the poles, both north and south. And it does this in a wavy line. And a couple of things happen. As it slides to the south, it drags cold air from the poles. So you get pockets of really cold air. But you'll also get, because it's wavy, you'll get these surges of warm air up in between. So you get things like, and I don't know whether you've noticed them over the last few years, you can have bushfires in California on the west coast. Then you go over the Rockies into the great sort of wheat belt of America, and they're having shocking frosts, which are killing all their crops. Had recently, a few years ago, where Greece was on fire. So Greece was really, really hot. This is in summer. At the same time, it was snowing in Austria. So you'll get these pockets of hot and cold beside each other. So that has much more of an effect on our weather. When you've got this really weak polar jet stream, we get much, much more colder weather because the cold weather comes away from the poles. There's two other things too, which I'm sure you'll pick up. There's what happens when our planet becomes a weaker magnet. It lets in what's called cosmic rays from space. Now, these are charged particles from space. They actually have a mass to them and an electromagnetic mass, and they hit our planet. And because we've got a weak magnet, we allow a lot more in. And they have two main effects. Number one, they nucleate the water molecules in clouds and cause them to clump. We get a lot more rain. And secondly, they actually stimulate the silica in magma and we'll get much more volcanic activity. If you think back maybe over the last 5-6 years, all that we've been having a lot of volcanic activity all over the planet. As we speak now, what are we just recently? We had the volcanoes on Java have been going off like crazy. You know, the east coast of Java is full of volcanoes, and they've been popping off. We've had Mount Etna, which has been crackling away. A few years ago, Mauna Kea in Hawaii blasted off. We've got them going, a lot of them going up on the west coast of Chile and stuff like that. So there's volcanoes been popping up all over the planet. So that's just an interesting thing. But that is one of the major causes of weather on our planet too. Low sunspot activity, cold weather. High sunspot activity, warmer weather. And that's just an explanation for it. So that's more for interest. It's not really, it's just another thing that explains weather and says and shows again, whatever we're looking at, it's nothing to do with carbon dioxide. So,
yeah, we've spent quite a bit of time, detailing that, and there's lots of valuable information there challenging the assertions of the IPCC and many others, all these other people that are trying, fear mongering and CO2 bad, and it's all because of that global warming and that. I mean, look, I've myself been very pushing back on it for a number of years once I've become aware, and you've detailed it really well, and you're obviously open. I mean, you're happy for people to be challenging you, reach out. This is all stuff that you kind of back yourself on. We spoke in the first episode, 30 years you've been doing this. When you first become aware of it, you've been really researching it, you've got your mind into it, and you're happy to take on anybody. And I remember Ian Plimer said the same thing. He says he'll take on anybody about and have anybody interview him to challenge it. So if anybody does want to reach out, they can probably do so. I can obviously put something in the Substack and wherever I upload it for people to reach out. I mean, genuine people that do want to sort of challenge your thinking, if you want to do that as well.
Yeah, it was interesting because when I sent you that piece, you out of interest, you stuck it through ChatGPT, and was interesting. What came back was, and I went through all the comments. They actually, it's funny to see how the internet now is working. I mean, I guess it works on the quantity of a particular stream of thought or opinion becomes its narrative. So if 90 people are saying the ideology of climate change is real, well, what ChatGPT kind of did was it reached a point of consensus and then tried to massage what I'd written to fit its consensus. It was bizarre, actually. I was because occasionally in life I do run into people. I'm never going to change their mind. They're ideologically, they're done. Doesn't matter what I say, they are not going to change their opinion, and that's their right. They're entitled to. But I found ChatGPT a little bit like this, except they were so wrong in some things. They accepted, funnily enough, every scientific point I made. They said they absolutely agreed with it, but they diminished its importance because they said consensus says, and they used things like that. They made two horrific mistakes. First of all, they said that, and this has been the basis of a lot of very early IPCC stuff, and certainly in the 1990s, it was thought that carbon dioxide stayed in the atmosphere for hundreds, if not thousands of years. And this is what ChatGPT said. The current consensus now is 4 years. I went outside ChatGPT into AI, and it came up with 5 years. So AI said no 5 years. ChatGPT said hundreds to thousands of years. So they picked a consensus, which is actually scientifically wrong, which was interesting. I've sort of discussed this with a couple of my geologist friends too, and they said, well, probably you're better going into, is it Grok?
Yeah, Grok's another one, yeah, which is the one that Elon Musk says. Yep.
If you come back to Grok and say, well, what about this, and give Grok some information, it will actually veer off and try and work it out. But they found, like me, certainly AI and ChatGPT pretty useless, because it's a summation of consensus rather than scientific fact. But they still didn't disagree, except for the couple of instances, as I said, like the amount of time carbon dioxide stays in the atmosphere. They didn't negate any of the science, but they diminished its importance. So they tried to bend the story to still fit the ideology and the narrative, which I guess is what we're all being faced with as we watch our planet and our country destroyed. Actually, that's not true. Our planet has turned the corner. It's only Australia that's being destroyed.
That's right. There must be some agenda there.
It is. We've got 60-70% of the first world countries no longer. You've got even Scandinavia. They don't use wind turbines anymore. They're all going to nuclear, like Finland and Denmark and Norway. They're all building nuclear power stations. They don't even try to use wind turbines. They tried and they saw how useless they were. So we're the only silly bunnies still installing the buggers. But there's a lot of. That is another conversation we could have too down the track. Why is that happening in Australia?
Oh, awesome, David. Well, thanks so much again for your time. There's definitely a lot of information there, so I'm hoping the viewers get a lot out of it. And remember, for those that have enjoyed the conversation, hit the like, hit the subscribe, and share the content if you enjoyed the conversation. And looking forward to having you come back on again, David, for a part 3 where we unpack a little bit more about the who, what, and why this might all be getting pushed. So thanks again for your time, and looking forward to seeing you again.
Thanks for having me, Mark. I guess if anybody has made it this far, you're well done. You. I'm sorry there was a lot there, but it's a story that is not taught in school. It's not discussed with us. We're never told. So it is one that should be told, I think.
Yeah, 100%. And look, people can take away from it what they can and what they want, but people can never say they weren't told the alternative than what's being propagated through media, our government, and international bodies. So, and you're doing your bit there. So good on you, David, and enjoy the rest of your day.
Thanks for having me, Mark.
No, my pleasure. Take care.
Okay, ciao.
There you go. That was David Denham, architect, who's been researching, the climate change narrative for the last 30 years. So stay tuned for when I catch up with him again, where we might talk a little bit more into detail about the who, what, and why it's being pushed, in particular here in Australia. So as I said, you like the content, click the subscribe and follow. And like buttons, but also if you have the means, by all means, feel free to contribute by buying me a coffee. So as always, I'm going to finish up with this little tune that I love, put together, come across, and as I say, God bless Australia. All the best, everybody.
For the next 3 minutes, I'd like you to see and hear something which we feel is rather special.
this God-given land of ours, Australia. This proud possession, our own piece of earth, that was built by our fathers who pioneered our heritage. Here in Australia, the land of our birth. God bless Australia, God bless Australia, all of the earth, strong and the free. It's our homeland, our homeland, cherished for eternity. God bless Australia, the land of the free. Here in Australia, we treasure love and liberty. Our way of life, all for one, one for all. We're a peace of embrace, but should danger ever threaten us, let the world know we will answer the call. God bless Australia, God bless Australia, home of the earth, the strong and the free. It's our homeland, cherished for eternity. God bless Australia, the land of the free. God bless Australia, God bless Australia, all of the earth, the strong and the free. It's our homeland.